Hi, I'm Warren Jones, and if you're listening to this, you've made it through the first of our 4 episodes covering terms related to the intelligent computer and stored purpose technology. No small feat. Here at Damson, after I speak, everyone typically runs over to the coffee pot. I don't know what that means. So please continue on if you can. If you have questions, visit our website at wjones.com, where we've got lots of illustrative material. And thanks again for joining us.
We'll also talk a bit about music, because music has a very interesting relationship with intelligence. One of the things we found as we were challenged by music early on, my co-inventor and business partner, Lana Robolski, one day we're sitting down and she said, you know, the system will never process music. No machine will ever process music. And I go, well, if it can process every type of information, it must be able to process music. And so I took an example of a song, and I'm starting to break it down information-wise. And I realized something's wrong here, because I couldn't figure out how to manipulate it to get it into the information structures that we were designing. And what I realized is that the logarithmic structure of music notation is exactly the same information structure we use for shape graphs. So there was no conversion required. So that may explain why we are able to appreciate music in different ways from other types of information, because we don't necessarily need to process it to enjoy it. It's already in a format that matches the shape graphs that are part of our primary means of understanding. And we'll talk briefly about how use of scientific music notation is possible in the creation of form data and in mapping shape data in graphs, in logarithmic graphs. And we'll go further into forms, because forms are very important. The ability to store information symbolically is the method that the stored purpose computers will be, you could use the word programmed, but that's how you define things. So for example, if you want to teach an agent how to maintain the grounds for a hospital, you teach it the forms for grass and for water, and the relationship between water and grass growth. You teach it how there are certain regions, and in context they are for walking, and other regions are not for walking. And there are a whole bunch of relationships that you place into these forms, and those forms then become the base information, the memory that's instantiated in an intelligent entity, like a lawn maintenance bot. So the forms are something that we'll spend probably a few episodes talking about them from various different directions. The metacomputer is our method for making these technologies, these concepts of existence in Emma, of the general intelligence algorithm, GIA, and of the multi-level cellular architecture of Mika, and enabling that to run on commercial hardware. Because from the very beginning, we both Lon and I, when we started the company, we had regular jobs. We were corporate IT leads. I was the chief information officer. She was the director of knowledge services. So we were very much concerned at that time about how do we solve real problems facing real organizations. So from the very beginning, as we started designing stored purpose, our focus was simply on a better enterprise computer. And as we made that better and then simplified it, and made it better and simplified it, we came up with an understanding of how intelligence works. But there was always this understanding that the final product would run on commercial hardware. So everything that we do and we talk about, and certainly if we're offline or if we have an opportunity to talk directly at any time, we can tell you very precisely how the software would work, what type of hardware it would work on, what kind of necessary components, controls you would need to make that hardware work. Because it is all ultimately real things. It just takes a while for us to build complete systems, and that'll be the next 3 to 6 years, much of our hours. Here's an example of just that very specific hardware. Well, we'll talk about the communications when you're using low power equipment in an intelligent metacomputer environment. And we actually did prototypes with IP6 and 802.15.4 because we were very concerned about the ability to enable a light bulb on level 1 cellular network to then be part of a fabric of lights that then might be part of various different components of a media system in a theater that then might be part of the business apparatus and other components of an intelligent theater system. So we wanted to make sure that all the parts actually could work and prediction could move quickly throughout the system using these commercially available technologies. And we found that 802.15.4 was very, very useful, along with IPv6, which is needed for lots of small devices. So this is just one of the technology implementations that we could talk about. We've done a lot of modeling of how the system should work. We're a small company. We can't afford to buy our own systems at this time, but we certainly can work through the logical and prototyping development. So what we've done in some cases is said, okay, if we finish the whole thing, we were able to actually buy devices for every part of a hospital. Here's what it would look like. Here are the various parts and pieces that would be needed. Here's how they would integrate. And not only have we thought through the various processes and documented it, in many cases we've created illustrations in the form of the graphic you see here, but as I'll show you shortly, also on our website. Here we're just showing a graphic of the symbolic network, and this is that intermediate layer between the commercial hardware and GIA, the general intelligence algorithm. And that it's sort of like a database server for intelligent identity that allows you to essentially instantiate the data, the hypergraphs that are an identity, sort of like reading in the genes, I guess, of a cell, you could sort of say, and then to create an agent. So that's what the symbolic network allows you to do, and we'll talk about that a bit. This diagram, and most of the diagrams you see here are available on our website. We typically publish the documents that have gone into patent filings on the website for public availability. We are limited, though, in those patent filings to the black and white line drawings. So we do actually add on the in this presentation here, you'll see a lot of text that you won't see in the final patent. So these are much more helpful, and we try to include some of this text on the website. But just to let you know, what you see on the website won't have any color and certainly won't have any of the 3D diagrams that we're able to present online in our podcasts. Here is a diagram of identity, or sort of the breakdown of identity in a multi-agent system. Identity includes regions of identity called purpose, and then subcomponents of identity called goal forms. And we've talked about the platonic form and goals a little bit. So we'll talk a bit about identity and the various different levels that you will see in identity that include the core, that is controlled or read-only memory. That's typically in a biological world, that's what would be in your DNA. Free will identity, that's what mammals and birds, what we have this ability to edit our identity and acquire things. The consumer society couldn't exist without a free will range of identity. And then learning, it's another aspect of where we can sort of build new forms by this coincidence detection and failure of plan. And we're able to grow new forms as part of identity. So that's sort of what's shown here, and we'll be able to talk about that.